So what is the role of mathematical modeling? First, let me emphasize the modeling means you are going to have your hand on to build your own model. It's not like what we learned in the previous 2 modules. You just use other people's model. So mathematical modeling will study the process and the methodology to build the mathematical models. And then to help you to gain the experience, we are going to provide a lot of case study projects. And the focus now becomes to transform application problems written in natural language to mathematics problem. And the procedure, the process of mathematical modeling give you a framework to build the models based on some sound scientific theory. We call it the first principles. And also build on your reliable domain knowledge, or sometimes it depends on experience. Nothing can substitute experience, by the way. Well, because this is anyway a mathematics class, the students come from all different majors. I try to minimize the demanding of domain knowledge. But when you talk about the application, they always apply to a particular domain. So the only choice I have is to minimize those complexity of the domain knowledge. And lastly, we needed to provide a meaningful test case. The difference from my mathematics modeling process is emphasize validation and the verification. You need to justify to your customer or supervisor why you think your model makes sense, why you think your answer is right. That's a difficult part. So let's start from a general criteria, a benchmark, distinguish from a good model and a poor model. By the way, we cannot say a correct model. There's nothing correct. It's just useful and a better. So because the model is a model, all models are fake, simplified. It's not real. Let's start from the 3C principle. The first is consistency. I think my definition here is very narrow. This only apply to the continuous model, and the consistency need to have equivalent unknown dependent variable and independent equation. True. That's only for the new continuous models. But you have other model, for example, consistency. You don't use the same letter x mean 2 different quantity. And you always use the capital letters for matrix and the small letters for scalars. You always put the arrow on the top, mean vector. That's also consistency for your using of a notation. That really tells you how well you are trained in mathematics. And other consistency. And you cannot give me 2 equations contradict themselves. Let me give an example. X plus y equals 3 and x plus y equals 4. That system is not consistent. And next, concise. That means you want to make it as simple as possible. And clarity. That means we are not allowed to have the ambiguous words. And you should write your assumption as clear as you can. Don't let the implicit assumption slip by and could make a lot of catastrophic accident. Other benchmarks for good model is the traceability. So any artifacts in your model should be easier tracing from upstream entities in the business domain to the downstream artifacts in the mathematics variables, equations. So the basic idea is you need to have a very good documentation process. Document why, where this assumption comes from, and this equation comes from, this variable comes from, what do you mean? And another issue is the model assumption should be always based on the first principle in science, or clearly specified the trade-off decision between the complexity and the accuracy. You know, of course, the more accurate you want your model to represent your real-world system, the more complicated you're going to get your model, and the harder to solve it. You always need to make those trade-off decisions, but you also need to document it. So the secondary benchmark of a good model all depends on documentation. If you are an experienced programmer, you know how important is this documentation, because you either spend your time to document what you write, or you spend your time to debug overnight. Don't mention when you have a huge team to work together, any thing without a documentation, basically nobody can follow. Okay, now we just give a little bit of general idea so far. Let's go to the classification of the mathematics model. We use all those keywords to classify models. You can think about a deterministic model and the probability model or stochastic models. If you think about a model as a structure for input here and the output here, a deterministic model, if you give a concrete input, and you are going to get the exact same output each time. And that's deterministic. A stochastic model depends on some randomness. If you give the same input the first day and give the same input the second day, but you may not get the same output because of the randomness of events. So it depends for the application. Of course, deterministic model is much easier. That's how you start your first mathematics model. Another keyword to classify is how you're going to model the time. There's a discrete model and the continuous model. A discrete model basically, you use the ticks of time to model your system. Such a system, you can have traffic light. You only have green, yellow, red. Don't have anything in between. And most artificial system, like our computer system, is a discrete system. If you want to model this algorithm, the most are discrete model. So a discrete model usually have finite states. And just like the traveling salesman problem, you look at the cities and you look at the graph from city to city. This is discrete. You did not put the time explicitly. However, in the natural phenomenon, most of the time you have the real time. That's a real time. And it's a continuous function. So the time domain is an interval. Like the t start from 0, maybe 100 units later. That's the real time. Such a phenomenon, you can have the temperature of your engine and your position on the road, so on and so forth in physical science. Another distinguish, that's the important one for this class, linear and non-linear. Well, if you recall all the models we talked in the previous 2 modules, I always start from linear phenomenon, and then we go to the non-linear phenomenon, and we have this process called the linearization. Eventually, most non-linear problem is solved by linearization, like the Taylor's series. So it really depends on the variable. Linear means a straight line. It's a proportional relationship. Give you an example. If you always drive 50 miles per hour, or a little bit of deviation, the distance you cover pretty much is a linear function of your speed, or a linear function of the time you spend. So in that case, the faster you drive, the more mileage you cover. But if you consider the money you spend on food have the relationship with your income, of course we know the more income we have, we may eat a little more money, spend more money to eat. But nevertheless, that's not proportional. If you earn $30,000 a year, you might spend 1/3 of your money by eating. But if you earn $1 million a year, you might only need to eat 1/10 of your money. So the function will be look like this. So this is the income, and this is the money spent on food. It's not going to be a straight line. Well, if it's linear, pretty simple in most cases. Non-linear, it's pretty difficult.